Hi everybody, I hope that all of you are doing well. Today we are gonna discuss very important topic, which is how to figure out the static friction and the kinetic friction. I know it was very hard for you to figure out that, and that's why I posted this recording for you. So today we will try to do that. I will explain everything theoretically, and then what I will do, we will try to do that experimentally. So I have a piece of wood right here. I have an angle scale right here, you can use it. And I have my favorite book right here. I will try to use it as an object. Yeah, so let's get started. And I will start, guys, talking about the static friction. So we know when the object is about to move, there is kind of friction right here is called max static friction or max static friction force. And also, guys, we know that the object on the incline with angle theta has weight mg, and this weight mg can be decomposed to y component and x component according to the coordinates that we have right here. And also we have the normal force, as you can see right here. Now this object is about to move, so it is not moving right now, it is about to move. That means we can use Newton's third law and create those two equations. Equation number one, along this x-axis, so we have max static frictional force is equal to mg sine theta. So this is equation number one. And here we have equation that describes the forces along y-axis. So we have the normal force is equal to mass times gravity equals sine theta. So this is equation number two. Now we know that the max static friction force is equal to mu s, the coefficient of static friction, times the normal force. And by the way, just to correct what I said before, guys, we are going to figure out the coefficient of static friction and the coefficient of kinetic friction. But now let's continue talking about the coefficient of static friction. So we achieved this equation, and that's great. So max static friction force is equal to coefficient of static friction times normal force, and that's equal to mg sine theta according to equation number one. Now, guys, we know that the normal force is equal to mg cosine theta, so we can substitute this in with mg cosine theta, and we will end up with this equation. Mu s is equal to mg cosine theta, and that's equal to mg sine theta. So we can cancel mg from here, and we will end up with mu s, which is the coefficient of static friction, is equal to tan theta. To correct, guys, what do we mean by coefficient of static friction? This angle right here represents the critical angle. The critical that makes this object just about to move. So we can't, for example, change this angle and then say that mu s will be changing. So this is one of the material properties, so we can't change it. But mu s is equal to tan theta. So when you have this critical angle that makes this object just about to move, so you can use this angle to figure out the static friction. So we are done with the static friction, and hopefully that's clear. I will move now and talk about the kinetic friction, as you can see right here. In this free body diagram that you can see right here, we have the same object, and we have the critical angle, but this object right now is moving. It is going down with acceleration A. So what are the forces that we have right here? So we have normal force, we have gravitational force that can be decomposed to mg cosine theta and mg sine theta, so that's great. And we have kinetic friction force. And we have the whole system is moving with acceleration A along this incline. So now we can create two equations similar to what we did before. So you can see that equation number one, which is along x-axis, is equal to mg sine theta minus kinetic friction force, and that's equal to mass times acceleration, because this book right now is moving. And the second equation tells me that the normal force is equal to mg cosine theta. So n here is the normal force, and m is the mass, g is the gravity, and here we have cosine theta. Theta here is the critical angle. Now guys, by substituting the kinetic friction force with mu k, coefficient of kinetic friction, times normal force, that will give me coefficient of kinetic friction times mg cosine theta, as you can see here, according to equation number 2. So now we can use Fk and substitute it with Fk or F sub k right here in equation number 1. When we do that, we will have mg sine theta minus mu k mg cosine theta. So that will give me mass times acceleration. Now you can cancel the mass on both sides, and you will end up with this equation that you can see. And also you can move mu k mg cosine theta to the right hand side and ma to the left hand side, so you will have this kind of equation. And also by cancelling the mass, you will notice that mu k, the coefficient of kinetic friction, is equal to g sine theta minus acceleration divided by g cosine theta. So this is a very important equation, and this equation can give me mu k. And this theta right here is the critical angle. This is the angle that makes this object going down. So at the beginning, you can see that the object from this free body diagram, the object will just start to move, but maybe after 1 second or 2 seconds, we can move to the next situation, which is this free body diagram, and you can see that the object right now is moving down under the influence of mg sine theta and F sub k, which is the kinetic friction force. And don't forget the acceleration, since it is moving down. So this is the theory. This is the theory. And now I will move to the experiment and try to explain that to you experimentally, guys. Let's move to the next part. I'm going now to raise this up slowly until we achieve the critical angle. Once we achieve the critical angle, I will fix everything. So we have 19 degrees. 19 degrees. This is the critical angle that made this book slide down. Now what I will do, I will try to test the incline again with this angle, the 19 degrees angle, and see if the object will go down. Now I'm fixing this book, I'm catching this book, so the book is not moving, but I will release this book and see what will happen, if that will work. Yeah, so that works. Now I will try to measure, guys, the time for this book to move from this point right here to that point right here. So why I'm doing that? I'm doing that to figure out the acceleration for this book. Once I know the acceleration, that can help me to figure out the coefficient of kinetic friction. So let's do that. I will try to measure the time. Okay, so I will do that more than one time and try to measure the time. I will release the book now, and I'm measuring the time right now. So 1, 2, 3. Okay, so now I measured the time 3 times. I will try to give the average, and I know the distance, and I will tell you now how to figure out the acceleration for this book, so we can figure out the coefficient of kinetic friction. Yeah, so let's move to the next step now. Hello everybody, now let's have some calculations from this experiment that we did. So mu s, as you can see right here, is equal to tan theta, and theta is equal to 19 degrees. So if we come here now, you can see that the coefficient of static friction is equal to tan 19, and it is equal to 0.34. So that's great. This is the coefficient of static friction. Now, let's move to the coefficient of kinetic friction. You remember that we measured the distance that the book went through. So you can see that this distance is 0.66 meters. And you still remember that we measured the time for this trip. It was 68, 66, and 72. Sorry, this needs to be 0 point. Sorry for that. And plus 0 point. And plus 0 point. So 0.68 seconds plus 0.66 seconds plus 0.72 seconds divided by 3. So that will give me 0.68 seconds. When we go back to this equation, so 2 times 0.66 meters divided by 0.68 seconds squared, so that will give me this acceleration, which is 2.85 meter per second squared. So now we know the acceleration. We can go to this equation now, right here. So we know that the coefficient of kinetic friction is equal to gravity sine theta minus a acceleration divided by g plus sine theta. When we do that, we will have these numbers that you can see right here. So 3.19 minus 2.85, of course, meter per second squared, divided by 9.27, also meter per second squared. So when we do these calculations, we will have mu k is equal to 0.037. This is a very small very small coefficient of kinetic friction. And you can see, guys, that we achieved this idea, which is mu s is greater than mu k. So mu k is always small. smaller than mu s. That depends on the material and other properties. Now guys, we can see that we can figure out if S max. So we know that if S max is equal to mu s times normal force, and normal force here is equal to mass times gravity cosine theta, so you can figure out ms max. And also you can figure out if k, so we know that coefficient of kinetic friction times normal force is coefficient of kinetic friction times mass times gravity cosine theta. So that will allow you to figure out if k. And if k is small, since the object is moving with this acceleration, which is 2.85 meter per second squared. I know the technique that I followed, which is just recording the time, is not efficient, because you know that we won't have that control to have precise time, measured time. So what I did, guys, I used this software. So we have the book right here. Yeah, so what I did, I followed the book movement from here to here. Yeah, and then I have those two plots, as you can see right here. Those two plots, position versus time and velocity versus time. And what I did, I fit the velocity versus time with a line, as you can see right here. So you can see the acceleration A here is equal to 1.241 meter per second squared. So this is great. And when I go back to the equation that we used to figure out the coefficient of kinetic friction and do those calculations, we will notice that the coefficient of static friction is equal to 0.21. I think using this technique right here is better than just measuring the time using the stopwatch. It is really hard to catch the accurate time. So yeah, so hopefully that's clear, guys. I did my best to explain this topic for you, and I did both of the ways. I did the first technique, which is just measuring the time manually and calculate the coefficient of kinetic friction, and it was 0.037. And you can see that there is a huge difference here when we use this acceleration. So the acceleration that was calculated manually was 2.85, but the acceleration here is 1.24, like 1/2 less than the calculation that was calculated manually. So yeah, and the coefficient of kinetic friction here with this technique, guys, is equal to 0.21. So it's still less than the coefficient of static friction, which is good. Yeah, so we did both of these techniques to figure out the acceleration for this book during the kinetic during the kinetic motion, with the kinetic friction. So thank you so much, guys. So now we are done, guys, and hopefully you did benefit from this session. We did experimental work. We derived some equations here, very important equations, and hopefully you will have everything to understand this topic. I know it is very hard, but I'm hoping that this topic right now became easy for you and you can see everything. So thank you so much, guys.